Alright, so we are going to continue the last few slides on consistency protocols that we were talking about last time, and then we are going to transition to a new chapter which is going to be on fault tolerance. Okay, remember that we are going through a steady clip. Fault tolerance will be about chapter 7 of the book. Okay, so we have covered fair bit of ground, so please keep up and read. Okay, even though exams are few and far between, there's no reason to wait until you have an exam before you start reading the material. Okay, it's important to keep up. Okay. So I'll give you a quick recap. What we were talking about last time was a whole slew of consistency semantics and consistency guarantees. Okay. And we started with strict consistency. We looked at several weaker forms of consistency, and towards the end of the class, we were talking about eventual consistency. Eventual consistency basically means that the system doesn't try to give any guarantees to the user about when, if some data is changed, when does it propagate to all of the replicas. Okay, so the idea is eventually all of the replicas will receive the updates, but there are no guarantees how quickly the updates will propagate. Okay. So that's the notion of eventual consistency. And I was talking about this notion of epidemic protocols, if you remember at the very end. Epidemic protocols are basically based on the theory of how epidemics or diseases spread among humans or animals. Okay, they spread through pairwise contact. Okay, suppose you're sick, you basically go and you have some interaction with a friend, you shake their hands or whatever. I mean, if it's infectious disease, then maybe it goes over there. But when you come to close contact with someone else, you spread the disease. Now, two people are infected and they can go infect more people, and you'll essentially start spreading the disease to a group of people. Okay? The same is true, or the same concept is true in epidemic protocol, which is a protocol to implement eventual consistency. Essentially, you have let's say one replica or a store that receives an update, and the goal is for this update to be propagated to all other replicas, so they are consistent with one another. And the way this is going to work is through this notion of pairwise exchange, where this store, which we'll call an infected store or infective store, will essentially pick another replica at random and try to push the update. It could also you could also have a pull-based protocol where you talk to a store and pull the update. Okay? So that's the basic idea. There are many different techniques to implement it, but just as far as history goes, it's important to remember how all this came about. Okay? So back in the late 80s, early 90s, there was a project called Bio at Xerox PARC, which was the research lab of Xerox. Okay? What they wanted to do was they wanted to implement a consistency protocol for mobile devices or mobile clients. Okay, remember, this is in the 80s, not today where mobile devices are prevalent. But they were thinking far ahead, saying, let's say your laptops or mobile devices, and you make a change to a file on the server, how do you propagate it to a client? Right? The basic problem that they had was that these clients were what they call weakly connected. Okay? What does that weakly connected mean? It means that clients are frequently going to disconnect from the network. They will not be always connected. So think of, you have a laptop. Okay, you are now maybe in the department, or you connect to the Wi-Fi network. Then you decide to go home. You close the laptop. You take a bus home. Okay? While you are doing that, your laptop is disconnected from the network. It's not connected to any network. So during this period, if there's an update on one of the replicas, you cannot propagate it even if you wanted to, because the machine is not even on at that point in time. Okay? So if you have environments where some nodes come and go, and mobile environments are a good example of this. Okay, they frequently disconnect from the network. Maybe you take, if you have a phone, you go on an airplane, your phone is going to be disconnected from the network. Okay, because you'll turn it off or you'll put it in airplane mode or some such thing. So in that scenario, you cannot actually implement any of the techniques we have been talking about, because all of those techniques have implicitly assumed that all machines or all replicas are always connected to the network. So if you want to send an update, you can do so. Okay? Now, if that fundamental assumption is no longer true, which means machines are not even up, okay, how do you propagate an update? You cannot guarantee strict consistency if the machine or a replica is actually not even connected to the network. How do you tell it that there has been an update? Okay? So in an environment where machines are weakly connected, okay, the researchers who are working on bio said we need a different approach. We cannot make any guarantees. Okay? So, and the reason is you cannot actually say when you can propagate an update because you cannot say when machines are going to be online to actually receive the update. So they came up with this notion of eventual consistency, which says only thing you can guarantee is eventually the updates are going to propagate, but we cannot make any guarantees. Okay? This was really the history of why eventual consistency came about. Okay? Now, in today's applications, eventual consistency is implemented even in scenarios where machines are not weakly connected. Okay? Simply because it's a very inexpensive and easy protocol to implement. So, although it was actually designed for a scenario where it was hard to actually provide any guarantees, now today it's implemented in any arbitrary system that I mentioned several examples of source code control and using cloud-based storage and to synchronizing with the cloud and so on. In those cases, it may not be the case that machines will be disconnected, but simply it's an easier protocol to implement. But the history of this goes back to the days when people were looking at providing consistency in mobile environments where devices get disconnected. Okay? Is that clear? Any questions on that? Okay. All right. So now we'll talk about two specific types of epidemic protocol. One is called anti-entropy and the other is called rumor mongering. Okay? In anti-entropy, server P picks server Q at random and both of them exchange updates. Okay? There are three variants of anti-entropy. One is that P is only a push-based protocol where P pushes all the updates it has seen to Q. Okay? Another is a pull-based protocol where P contacts Q and pulls updates, saying what updates have you seen that I haven't sent me those updates. Okay? And the third is that you have to do both. Okay? P pushes to Q whatever new changes it has seen and pulls from Q whatever new changes Q has seen. Okay? So you have both push and pull going on at the same time. Okay? Now, so that's the approach. So every so often you toss a coin. Okay, meaning a server is going to toss a coin, pick another server at random, and the servers will communicate with one another. Okay? And it could be push-based, pull-based, or push and pull-based. Okay? And in this case, this is how updates are going to spread. So as soon as you make an update on any replica, after a while that replica will contact some other replica, it will push or pull the updates, and then it's going to keep on spreading through the system. Okay. Now, here is a simple claim, and we'll discuss why. It says a pure push-based approach is not going to allow you to spread the updates quickly. Okay. The question is why, and it says a pull or an initial push with pull will work better. Okay, can you think of why, if you picked an anti-entropy approach and you only said I'm always going to push, okay? And then the answer is that the pure push-based approach is not going to help you to push the updates to all of the replicas. Initially, it will be successful, but after a while, its effectiveness will diminish. Can you think of why that may be the case? Yes, Patrick.
So as the updates become more propagated throughout the system, the probability of to choose to push to a machine that doesn't have the update becomes less and less.
Okay, so that's exactly right. Initially, a push-based approach is a good one. As soon as you see an update, you're the first replica to see an update. No one else in the system has seen that update. So you can pick any other server at random. It wouldn't have seen that update. So an update will spread very quickly because the probability that you will find a susceptible store, which is a storage server that hasn't seen the update, is very high. Okay? Because only a few machines have seen the update, no one else has seen the update. So you can pick any server at random, and your update is going to spread quickly. But after a while, okay, a large fraction of your server pool is going to get infected. They would have all seen the update. Now, if you keep tossing a coin and pick another server at random, the chances that you pick a server that's already seen the update is very high because a large fraction of them have already seen it. There's only a small group that hasn't seen it. Okay? So the effectiveness of a pure push-based approach is very high at the beginning, and it's going to quickly drop off as a larger and larger fraction of servers start seeing the updates. Okay, so what do we do to get the updates to the remaining few servers? Okay, so at that point, you will have to actually do exactly. The answer is already here. So you have to combine a push and pull. So when you have a scenario where a large number of servers have already seen the update, what's a way to actually get the remaining servers to see? You combine push and pull. You have each server also uh, contact some other server at random and pull data from it. So in this case, the small group of servers that hadn't seen the updates are going to toss a coin at random and contact another server and say, do you have any new updates that I have not seen? The chances of those machine that server finding a server that's already infected is high because most of the other servers have seen the update. So it's very likely you will contact the server that's already seen it. Okay? So if you want to spread the update quickly, initially it's better with that you have a push-based approach, but in the later stages, a pull-based approach becomes more effective. So combining both approaches is the best option to ensure that your update actually gets to almost all of the servers. Because this is a randomized approach, you can never guarantee that you will actually spread it to 100% of the servers, but with high probability, all the servers are going to see the update if you combine push and pull. Is that clear? Okay. So that's anti-entropy. The other type of epidemic protocol is called rumor mongering, and this class of protocol is also called gossip-based protocol. Okay, if you actually search for gossip-based protocols, you will again see lots and lots of papers that have been written on it. There are many different variants of gossip-based protocol, but by and large, all of them work the following way. Okay? So here is basically how it works. So once server P receives an update, okay, it is going to try to push the update to Q. Okay, so this is a push-based protocol. Okay, now if Q has already seen the update, so if you toss a coin and find server Q at random, and if Q has already seen the update, then you are going to stop spreading this update with a probability 1 over K. Okay? Otherwise, you are basically going to continue to spread the update. Okay, so the best analogy is to think about how rumors are going to spread. Okay, so let's say initially you have a hot piece of gossip. Okay, then you want to basically tell everyone you know about this gossip to spread it. Okay? But after a while, as the gossip spreads and you think that everybody kind of knows it, you're not going to go around, pick up the phone and say, have you heard about such and such? Okay, you're going to stop saying that, okay, now everyone knows it, why bother? Okay? Same is true here. Okay, so this is essentially how you spread rumors or you spread gossip, which is initially you're going to try hard to push. Okay, but once you now start seeing that when you contact a server at random, it's already seen that update, you're going to toss a coin. Okay, with probability 1 over K, you're going to say, I'm going to stop. And this K can be chosen any way you want. Okay, that's your back off probability. That's the probability with which you stop. Okay, so if you want to aggressively stop, you can basically set K to be very high, okay, or very low, so that 1 over K is close to 1. So as soon as you see that some other server has seen your update, you back off saying, I'm done. I'm not going to spread anymore. Other servers may still be trying to spread, but eventually they will all back off aggressively. Or you can set 1 over K to be a very low value, which means even though other servers are seen, you keep trying, saying, maybe this server saw the update, but there may be others that have not, and you keep trying. Okay? So you can probabilistically vary K, and that will tell you what the back-off probability is. Okay? Now, if you have such a randomized protocol, okay, you can analyze the protocol, and I'm not going to do it here, I'll just give you the final result. And the protocol will say that the probability that some server has not seen the update at all is going to be this exponential probability. Okay, where e to the minus K plus 1 over 1 minus S is the probability that you're going to stay susceptible. Yeah, so you'll say that it's exponentially small, but there is a non-zero probability. That's the way to keep that in mind. Okay, it's 1 over e to the power something. So that's a very small probability, but there is going to be some chance that you will actually never see the update. And the reason for this is a push-based protocol with a back-off probability. Okay, so as more and more servers see the update, okay, you will basically keep tossing a coin and start backing off, and it may be the case that all servers that have seen the update have backed off, but there are still a small group of servers that did not see the update before they all stopped spreading the gossip. Okay, is that clear? So this is a randomized approach, and since it's push-based only with a back-off built-in, which says I'm going to stop once I see that others have seen the update, there will be a non-zero and small probability that some small group of servers never see an update. Okay, you could have, of course, combined that with pull and try to address that and so on. That is how you make different variants of gossip. But the pure gossip protocol is push-based with a random back-off probability. Okay? Any questions on this? Okay, so now a few small implementation details. Okay, so I've spoken so far about spreading updates. Okay? Now there may be data items that are not updated but simply deleted from the system. Okay, so question is, if you actually go into a database and delete a record, okay, you ought to now, that's a change that also has to be propagated to all other machines in the system. Okay. Question is, how do you go about doing that? You can use the same approach. You can randomly contact another server and say, this record has been deleted, this file has been deleted, or this data item has been deleted, go ahead and delete it. Okay. Now that server can delete it, and you can start spreading this delete chain through the system. Okay, just as think of a delete as a special type of an update where rather than changing the value of a data item, you completely eliminate the data item, eliminate the record. Okay. That's one way you can actually use epidemic protocols to make deletes. However, unless you do this carefully, you will see some problems. Okay. So let's say, just going to draw a small picture here. Let's say there are two servers, A and B. Okay. A has data item X and B does not have data item X. Okay, let's say that B is the one that's already deleted the data item. Okay, so it's gone from. Now, if A and B talk to one another and do pairwise exchange, and A asks B or B asks, say, what data items do you have? Can you tell me what they are? You may see that unless you are careful, okay, this data item X that was deleted may regenerate. Okay, because there is no way to distinguish between a deleted copy and no copy. Okay, once you delete a file, you don't no longer have any trace of it. Okay. Now, if you contact, let's say it's a photo, you deleted a photo and you're trying to sync with two devices are trying to sync. One has deleted the photo, other hasn't. They talk to one another and say, what photos do you have that I don't have? And you'll say, here's a photo that I have, and you may actually send it back, not knowing it was deleted on the first machine. And it may regenerate. Okay, is that clear what I just said? Okay, distinguish, once you delete something, if that's all the traces of that item ever having existed is gone, if you contact another server which still has that item, it hasn't deleted it, that item may regenerate. Okay, so you have to be careful in how you implement a delete operation. It seems very straightforward, but you need to basically account for this case. The way you are going to account for this trace is, even though you delete a data item, and if you don't simply delete it, you keep track of the fact that you have deleted it. Okay. This is called keeping a death certificate. Okay. So you may actually delete the file X, but you keep a small piece of information here saying I deleted X. Okay, that's called a death certificate. So now if A and B try to do pairwise communication, okay, and A tries to push to B, B will say, no, don't send me X again. Instead, go ahead and delete it, because it's not that I don't have X, it's that I deleted X. Okay, so you keep track of which items are deleted through a simple list, which is just a set of related items. Okay, that this way, you're not going to regenerate items that have simply disappeared, okay, from your system because some user deleted it on some machines. Okay. So this is just to show you that epidemic protocols, while they work well, When you have things like creation and deletes, you have to handle those cases carefully. You don't want to not do the right thing and have deleted data reappear and whatnot. Any questions on this? Okay. So now one thing I should mention before I continue is although all of these epidemic protocols work well in general, okay, there are scenarios where you may still see some problems. And one common case where problems arise is two users modify the data item on two different servers at this more or less concurrently. Okay, and then you don't know which one is the right one. Okay, and then you're going to have a right conflict. Okay. This scenario is going to happen often. You may have seen it in source code control, where two users have modified the same source file. That's going to result in a conflict. If you use Git or SVN or any of this, you will see that you try to make the same change to the file because there's no locking. Any user can modify whatever data they want. You're going to get a conflict. Okay, you can do the same thing by if you have a calendar application that is also synced across devices. If you go to two different devices and add two different appointments at the same time, that's going to result in a conflict as well. Okay? This often happens when some people actually delegate or provide access to a calendar to their administrators or secretary and so on, and you put an appointment at some time, your secretary, not knowing that you made a booking, also puts an appointment at more or less the same time, then there is a conflict. Okay? Because when you make this change, you don't know what else has happened in the system. So in all of these epidemic protocols and eventual consistency, right conflicts can still occur. Okay, in general, if you make modifications to different data items, you will just have those changes propagate and everything will sync up. But if you make changes to the same data item while these changes are still propagating, you're going to result in a right conflict. And those have to be handled by the user. There's no way for the system to figure out what is the right approach. So you can't override this change. You can simply flag the user saying, here's a conflict. Right? Two updates are made to the same data item. Go and reconcile or resolve this conflict. And then the user has to step in and do something to either merge the changes or decide which appointment takes precedence and so on and resolve the conflict. Okay? Is that clear? Any questions on this? Okay. So I'm going to talk a little bit about some ways to implement many of these protocols that we talked about, starting from our consistency method that we talked about, starting from strict all the way to eventual consistency. Okay, and the approach that I'm going to talk about is very high level and general. You can adapt any of these consistency semantics to actually work with these protocols. Okay. And there are two classes of them. One is called primary based, which assumes that there is a master. Okay. In a primary based approach, there's always a master to which changes are made, and the master's job is to replicate or send these changes to all the slaves. Okay. So it's a master slave scenario. The other approach is where there is no master. You can make a change to any replica, and that replica has to then propagate that change to all other replicas. So there are these two classes of protocols. I'm going to show you some pictures which very simply demonstrate how this is going to work. Okay. So here is this is, I think, a remote write protocol, which is the second one. Okay, so I'm going to show you what's going to happen here. So here is a single server for data item X. It's the master for X. Here are two clients. They're connected to two other replicas. So what you will see by and large, what's happening is whenever write comes in, the write eventually has to go to the master, and then the master is going to send it off to other clients, other replicas. Okay. There's a lot of acknowledgements and all of that here that you can ignore this picture taken from the book. But essentially what it says is, if you send a write in a primary based protocol to any of your local replicas, it has to send it off to the primary. Is the primary job then to actually send it off to other machines. Okay, so that's basically, when we look at distributed file systems, we are going to look at this approach first, where there is going to be a master server and there will be replicas. Okay, and then if you make a change to a file, you have to always send it to the master first, and then the master can then either send those changes to the replicas or send invalidates to the replicas. Okay. This is just the next step of the protocol where the write came in, and now you see that that write is being sent to this replica, it's being sent to that replica. You see all of this write propagating. So initially the write comes into the master, and the master sends it all off to the replicas. Okay? And then all of the semantics are going to depend on when the write is propagated. If you are strict, then you try to send it as soon as possible. If you have weaker guarantees, you can delay when the writes are actually sent off. In eventual consistency, you can wait for an arbitrary period of time before the writes are sent off to other replicas. Okay? So that is going to determine how you actually take a specific semantics and layer it on top of a primary based approach. Okay. So here is a different approach, which is called a local write approach. In a local write approach, you can actually make changes at any copy. Okay? There is no master anymore. You can make writes to your local copy, and it's your local replica's job to send it off to all other machines, which is essentially what is shown here. Okay? Now this shows you a special case that you will also come back when we see NFS in the context of distributed file system. We will see this approach as well. Okay? So in this case, you have one copy, one primary copy that's floating around. Okay, so initially that primary copy is here. Since changes are being made here, you basically transfer the copy here. That copy arrives at this server. You make those changes, and then the changes are sent off to all other machines that have an extra copy. So in this case, your local replica takes over as primary. There is no single primary. Okay, the primary keeps changing, and the primary data item also moves around to wherever the writes are happening, and then the writes are propagated to all other machines. Okay. In the previous case, the primary is static. It is this machine. Okay. In this case, the primary keeps changing. So you basically say, initially there's a write request. You basically forward the request to the server. The server delegates to you, say you take over. You can process the writes locally. You don't have to send them to me. So you process the writes, and then once those writes are processed, you do have to send them to all of these other replicas. Okay, which is basically what is shown on the next slide. Okay, lots of arrows, but essentially what has happened is the write came here, and then it's been sent off to all other machines. Okay. Again, the timing of when you send it off will govern what consistency guarantees you give. If you send it immediately, your guarantees will be stricter. You delay it, you may get eventual consistency guarantees. Okay, so those are two primary based protocols. Now I'm going to show you a replicated write protocol, which actually says that there is no primary at all. Okay, in the previous case, there was a primary. In one case, it was static. In another case, it was changing. Okay, now I'm going to show or explain a technique where you do not have any primary at all. Okay. In this case, we are going to use voting to decide what has happened in the system. Okay. Because there is no primary, there is no way to figure out who has the right. So we are essentially going to use a voting based approach to determine what is the latest version of a file. Okay. Different machines have different versions of the file. Some have seen some writes, others have not seen some writes. Okay. And the question is, if a read request comes in and you want to return the results of the most recent write, how do you go about it? You're going to have to basically use voting to figure out which is the most recent version at all, and then use that to send back a request. Okay. So these kinds of protocols are called quorum-based protocols. Okay. So essentially, you need a quorum, which is quorum is basically a set of machines that have to agree. Okay, that have to all say yes, this is the most recent version. Okay. So you're going to use voting to determine what has happened. Okay, and I'm going to explain what the technique is in just a moment. But there are two. Just before we do that, we'll come up with some definition. So we'll assume there are two quorums: a read-based quorum and a write-based quorum. Okay, a read-based quorum, which we'll denote by n of r, is the number of servers that you have to ask, and they all have to agree in order for you to successfully process a read. A write-based quorum is the number of servers you have to send a write to, and they all have to process the write successfully before the write finishes. Okay? And we'll see there are different ways to pick the read and write quorum. Okay, this is just a number. So in this protocol that I'm going to talk about, the write quorum has to be greater than half the number of servers. Okay, so you want a strict majority. So you always want to send a write to greater than half the number of servers. Okay? And you can pick the read quorum any way you want, so long as the NR plus NW is strictly greater than N, which is the total number of servers in your system. Okay? So when you make an update, you contact at least N by 2 plus 1, which is NW servers, and get them to agree or to do the update, okay? Which is to increment, let's say, the version number and so on. And when you do a read, you contact NR servers, and they all have to agree. Okay? I'm going to explain this with examples, so all of this is clear. Okay? So here are 3 different scenarios of how you have implemented. So we'll assume that there are 12 servers A through N. Okay? 12 servers in the system. Okay? Each data item is replicated. Let's say it's just a file. Each file is replicated on all of those 12 servers. Okay? We'll also assume that there's a version number with each file. Okay? That allows you to, or maybe a timestamp with each file, it doesn't matter what it is, which says when was the most recent update that that server has seen. Okay? So we are going to configure the system 3 different ways. Initially, this example says the read quorum is 3, the write quorum is 10. Okay, what does that mean? If you wanted to do a write, what would you do? What does quorum mean?
More than 5 of those servers in the right quorum have to agree.
Okay, so I said that you have to pick the read and write quorum in this way. Okay. So I said write quorum has to be strictly greater than half the number of servers. It can be any value, okay, but you have to at least have more than half. Okay. So we picked the write quorum to be 10. Okay. What that means is any time any client wants to make an update to the file, you have to pick 10 servers at random among these 12 and send those write to all 10 servers. So here is the update that I have made. Okay. So that's what write means. Okay. Write quorum of 10 means every write has to be sent to 10 of these servers. Pick those 10 any way you want. Okay. So, but 10 servers have to see the write. Okay. Read quorum is 3, which says you pick any 3 servers at random. Okay. You ask them for the file. You compare the version of the file. If it agrees, then you can say you're guaranteed that that's the most recent version. Okay. If they disagree, then you can again repeat. You pick another 3 servers at random, and essentially they're going to vote by saying this is my most recent version. If the voting agrees, then you're done. If it doesn't agree, you're not done. Okay. And that's exactly what is shown in this example here, which is essentially saying this dotted line are the 10 servers you picked for the most recent write. Okay. Some client updated the file, you essentially picked C through L, and those are the servers that saw the write. Okay. So all of those servers are the most recent version of the file. Okay. Now let's say some other client wants to read the file. It has to pick 3 servers at random. Okay. The worst case is it's going to pick A, B, and C. Okay. So ask A, B, and C for the version of the file. Question is, will those versions match? Okay. They shouldn't, because A and B did not see that update, but C has seen the update. So C's version will not match A and B's version. So you have a mismatch. So you will say, okay, I cannot send any of these versions back to the client because the versions don't match. Okay. You pick another 3 servers. Okay. And eventually you will pick 3 from the servers that were in the right quorum, and those versions will match. At that point, you can return the results, and you are confident or guaranteed that that's the most recent write. Okay, is that clear? Okay, here is another example. Okay. Here we set the write quorum to 6, read quorum is set to 7. Okay, that means whenever you make a write, you have to send it to 6 randomly chosen servers. Whenever you want to do a read, you have to pick 7 servers, and those servers have to agree. Okay, so the dotted lines here show you the servers on which a write has been performed, okay, which is essentially this D, H, L through I. Okay, so those servers have seen the write. Now let's say you want to read the file. You are going to pick 7 servers at random. In this case, you pick these 7 servers. Okay. Question is, are they going to agree? Okay, you picked in this case 6 servers, which is A, B, C, E, F, G that did not see the write, H that did see the write. Okay, H is going to disagree with the rest. Okay. If you have a disagreement, then you say that I don't know what's the right version, they are all disagreeing. So you pick another 7 servers until you find agreement. Okay. Question is, in this case, are you going to find agreement? Okay, you couldn't find agreement because there is no way to pick 7 servers, all of them who will actually see the file, see the version of the file, because there are only 6 servers that have even seen the write. So no matter how you pick, there will be at least one server that hasn't seen the write, it's going to disagree with the others. Okay? So two things to keep in mind. One, nothing bad is happening in that you are not returning an old version of the file. Okay, so there's always some server that disagreeing, so you will keep trying. Okay. Second point is nothing good is happening because in this case a read request will never succeed because there is no way you picked the read quorum such that there's no way you are ever going to find 7 servers that have all seen the write because the write was only processed by 6 servers. Okay. Question is, why did this happen? Okay, so in this system, if you configure your system this way, you will never, you send a read, the read will never return with anything. So you keep trying and you'll never find a set of servers that all agree. What do you think went wrong in this case? Yes?
The number of write servers is not larger than half the number of all the servers.
So that's right. So you'll see that we violated a property we set for ourselves. We wanted 2 properties. We wanted NW to be strictly greater than half the number. So we set it to exactly half. Okay? It should have been at least 7. Okay? And the second thing is, once you set that NR plus NW can be greater than N. Okay? That is actually, we have 6 plus 7 is greater than 12. So that property is satisfied, but we did not satisfy this property. So you need to pick your number of servers carefully. Okay? Otherwise, you will have trouble. In particular, if you set the write quorum to be less than majority, bad things can happen. Okay? Which means that you may actually get inconsistent results and things like that. Okay? So you want the write quorum to be always strictly greater than majority. Okay? But to also succeed, you want to also have this other property NR plus NW greater than it. Okay, those 2 properties were satisfied here. Okay, we set write quorum to 10 and read quorum to 3 so that it worked well. Okay. Here's the third case where we have actually set the write quorum to be 12, the entire set of servers, and in that case we can set the read quorum to 1. Okay. So every write is going by default to all servers immediately. You make a write, you have to send it to all servers have to process the write, and then you tell the application your write is completed. So all servers always have the most recent version of the file. Okay. In this case, by default, you can set NR to as small as 1 because NR plus NW is still greater than N in this case. So this technique, this particular special case is going to be called read once, write all. You always write to all. Okay, you can then go and your read can hit any server. You don't even have to check with other servers. Because if you set NR to 1, the voting is yourself. You are not even comparing with anyone. But you are guaranteed that you are going to get the most recent version of the file, even by checking with only one server. Because you are ensuring that every write has gone to all servers, so there's no need to check. Okay? So this is most efficient in terms of reads, because you can just send it to any server you care about, and whatever it returns is guaranteed to be most recent. But it's most expensive in writes because every write has to go to everyone. Okay? Now you can pick NR and NW any way you want, okay? So long as it satisfies these 2 properties. Okay? You are going to ensure that bad things don't happen. And by bad things we mean that a read is not going to return an old file version of the file if a newer version has been produced in the system. Okay? You'll always get the most recent version. It requires you to vote and so on, or in other words, the read quorum has to agree. So if you pick it this way, you are going to be good. This technique is called Gifford's quorum-based protocol, as is mentioned here, named after Gifford, who proposed it. It's a simple voting-based approach to ensure consistency in your system. Okay? Many tech systems do use something like this, where you use voting to decide what is the most recent version. Okay? So in this case, as you can imagine, you don't have to propagate writes and so on. You simply send the writes to a large enough pool so that the reads are going to succeed. That's all you're doing. Okay? Question is.
If NW is set to 7 and the number of read servers are set to a value higher than 7, I mean in case B,
Yes.
then there will always be a conflict in that.
Okay, so question is, let's say NW, let's take this example. NW is set to 7, okay, and you pick NR to be 8. Okay, so NW is greater than half, okay, NR plus NW is greater than N. Okay. You will see that the technique works from a safety property. There are two properties you want in any distributed system. It's called safety and liveness. Okay. Safety means nothing bad happens. Liveness means something good happens. Okay? So the safety property is not violated. Even in this case, the safety property was not violated because you are essentially sending it to 7 servers. Okay, and so you will basically ensure that a majority see it, but you picked your read quorum badly. You picked your read quorum to be greater than the write quorum. That essentially ensures that you will never find enough servers that have all seen the write. Okay? So your reads will never succeed. Okay, but your reads will also not return your old value. Okay, so essentially, if you pick it badly, you are going to ensure safety but not liveness, which means you will not succeed, but nothing bad is going to happen either. Okay, nothing good is happening. Your read is sitting there and just trying over and over again. Okay, so if you want safety and liveness both, it also goes without saying that you pick this to be a majority, but pick your read quorum to be smaller than the write quorum. The read quorum is bigger than the write quorum, you are going to have this case where there will be at least one server that has never seen the update and you are not going to succeed in finding the most recent version of the file. Okay? Is that clear? Okay. So I didn't implicitly say that NR has to be smaller than NW here. Okay, but if you don't pick that, you are not going to succeed in processing reads, but reads are not going to give you anything bad either. Any other questions here? Okay, so that's Gifford's quorum-based protocol. It's a voting-based approach. We are going to come back to voting when we talk about fault tolerance and Paxos in a little while. Okay, so voting is going to be an important aspect of many important properties in distributed systems. One, we are going to talk about agreement. We are going to talk about consensus. We are going to talk about fault tolerance. A lot of them are going to be voting-based. Okay? We encounter voting when we are doing leader election and so on. Okay? Here is another case where you are essentially looking at voting. This is a very simple approach where you have to have the participants agree on something. Okay? So essentially, a read is going to succeed when there is agreement. Agreement says all the servers of the read quorum agree that this is the most recent version of the file. Okay, this is an important concept. We encountered it in the context of consistency, but agreement is actually a very important concept in distributed systems. We are going to keep coming back to this as we talk about fault tolerance. This is the first time we've encountered this notion of reaching agreement. Okay, so we'll come as we talk about this, we'll see that this is actually an important issue. We're going to quickly talk about replica management, not a whole lot because this is something we'll talk about in fair amount of detail when we do the World Wide Web chapter. Okay, so a lot of our consistency discussion is focused on what kinds of guarantees to produce across a set of replicas, but there is also the important problem of if you have replication at all, there are many things to think about. How many replicas would you put in the system? Where would you put these replicas? Okay? These are all important issues. Okay? If you want to replicate, are you going to keep 2 copies of something or have 2 servers? Are you going to have 3 servers? Are you going to have 12 servers like we talked about? What allows you to make this decision? What's the degree of replication in your system? Okay? First question you will have to answer. Okay? Second question is, if you have n replicas, how are they configured? Are they all machines that sit in a cluster in one location? Are there replicas you place in different locations? Okay? They give you different properties. Okay? You can, if you keep them all in one location, their set of servers, if one of those servers fails, some other server can take over. Okay? If the entire cluster catches fire, all servers have gone down. Okay? But if you place these replicas in different locations, a natural disaster of any sort at one location does not impact other replicas. Okay? So you may have fire, you may have network outage, power went off. Okay? There's flooding in the building or some such thing happened. Many reasons why an entire cluster can go down. Okay? So there's local replication, there is geographic replication, wide area replication. Okay? It all depends on what goal you want to achieve from your system. Okay? You may also want to place replicas at different geographic locations if your users are spread across different geographic locations. Okay? One simple thing is you place one replica in each continent. You have users in Asia, you put a replica in Asia. You users for your application in Europe, you put a replica in Europe. You have one in the US, you put one in North America. This allows you to also give lower latency to your users. If all the replicas are in one place, users that are far off will see a long latency to get to your servers. Okay, let's say you are a very popular social media application or game. You put lots of servers, but you put them in one location. Okay? So you have enough server capacity to satisfy all your users, but some users are nevertheless going to see poor performance simply because the network distance to send your package to the servers is large. Okay? So for these reasons, you may want to do geographic replication. So there are many different issues that come up. How much to replicate? Where to put the replicas? How to spread them based on where the users are? Okay? All of these issues we'll talk about when we talk about the web. I just want you to keep this in mind that there are two aspects to replication. There's the consistency aspect and there is the degree of replication and the replica placement aspect. We only talked about consistency so far. Okay? This is an important aspect as well, but we are going to look at it not in general, but in the context of the web. Okay, so with that, I'm going to, as I said, we'll come back to this in chapter 12. So very quickly, we have done with consistency, techniques and aspects of replication. The thing to keep in mind is we have a set of guarantees one can provide to you to your users that those are the consistency semantics. They go from strict, which give you good guarantees, to eventual consistency is a very weak guarantee or no guarantee at all, and there are lots of techniques in between. If you are to design an application that involves replication, and which you will in lab 3, you will have to decide what consistency semantics matter. Right? Which of these semantics are you going to provide? How are you going to implement it? Okay, so all of these are going to be things you decide based on what kinds of guarantees and what is acceptable to the user and so on and so forth. Yeah, but as this comes up in any applications design. Okay, so with that we are going to switch gears. We have about 20 minutes remaining. I'm going to talk a little bit about fault tolerance. Okay, we are switching gears now. Okay, we are going to look at how replication can help us deal with faults. Okay, consistency was just the problem of we have replicas, so we keep them all synchronized. Now we are going to see if some of these machines go down, what can you do? Okay. So we are going to start slow. I'm going to define what kinds of faults exist and give you some very simple ideas on how replication can help you overcome faults and so on. And next time we are going to look at in fair amount of details how to get agreements in the presence of faults, all of these important problems of how to recover from fault. Okay. So we'll start with some basics. Okay. So if you have a single machine and you have a centralized application, okay, you have an all or nothing property. Either your machine works or there is some problem and it doesn't work. It may have crashed, there may be a software bug, the network has gone down, the disk died. Any of these will just cause the application to stop functioning. So it's all or nothing. Either it works or it doesn't work. Okay. But when you have a distributed system, that is no longer the case because you have multiple independent machines in your system. Okay. You have a system of n nodes. Okay. Now if some subset of them fail, many things can happen. One is that there is no impact on the application. You have designed your application such that even if subset of the nodes fail, the other nodes take over their jobs. Okay, so application continues to run as if nothing has happened. It may operate in degraded mode because there are fewer servers and there's less capacity, but the application continues to run. Okay? Or you may not have implemented fault tolerance at all. Okay? You have n nodes, but you have some functionality of your application that's not replicated. So if that node goes down, you're out of luck. Okay? Your system doesn't work. Okay? Simple example is, let's say you want your users to log into your application. Okay? You have a username and password before you let them access your application. Okay? Maybe your application itself is replicated, but if your username passwords are stored on one machine in a password database, that machine goes down, your application may be running fine, but no users can log in. Okay? Because your password database has become a single point of failure. So you may often have scenarios where you have n nodes that are serving an application, but there are still functions that are single points of failures. Okay, so if that particular machine goes down, even though you have n nodes, your application may fail. Okay. So the proper way to design a distributed application with fault tolerance properties is to ensure there's no single point of failure. Any function can be done by any machine. Okay, or any machine can take over any function should the primary or some subset of the machines fail. If you do that, then your application will actually work despite failures. Okay. So the question we are going to ask is, we'll assume there are some partial failures. Okay, of course, if all n nodes go down, nothing can be done. Okay. But let's say some subset of the nodes fail, then how are we going to make this work? Okay. Now, first thing I'm going to mention is there are certain fundamental properties, okay, that will require us to implement fault tolerance. Okay, and that property says if you have n nodes, as n grows, okay, probability that some subset of the nodes fail starts approaching 1. Okay, this is fundamental property of machines. Yes, sir. Just to emphasize this one more time. Okay, I'm going to say, let's say your n nodes in your system. Okay. As n is going to grow, which means n is going to, I said n goes to infinity, but let's say you have 100 machines, you have 1,000 machines, or you have 10,000 machines. As this n is going to keep growing, okay, the probability that there's at least one failed machine starts approaching 1. And this simply comes from this very simple observation. Okay. The probability that there is a failure in your entire system is the probability that at least one machine is down, which is 1 minus the probability that no machines are down. Okay. So what that basically says, the reason this is true is this is equal to 1 minus p to the n. If p is the probability of any machine failing. Okay. And so 1 minus p to the power n is the probability that there is no machines are failing. Okay, a simple probability. Okay, now, as n goes to infinity, p to the power n is going to go to 0. Okay, so this term is going to grow to 1. Okay, so what does this tell you? Okay, we have not done any systems work. It's just simple probability theory is telling us if you have large number of components in your system, the probability that any one component is going to fail at any instant is going to start approaching 1. Okay, so what does this say? Okay, so that says that in a large system, okay, failure is not going to be an uncommon case anymore. Failures are going to be the common case, which means that at any point in time, there will never be a scenario where all machines are up. Something or the other will always be down for some reason or the other. Okay, so if you have a cluster, a large cluster, you will know exactly what I'm saying, or you have any experience. You have a machine, let's say a cluster with 1,000 nodes. Some small number of machines will be down for some disk has failed, something went wrong, OS crashed, machine overheated, some problem or the other is going to crop up, and because even though these may be independent, simply because of this probability, okay, you are going to have a scenario where some nodes are down. Okay, what this also says is, in very large systems, okay, you can never assume that all machines are up. So you have to incorporate fault tolerance into your system. Always assume that some small number of nodes are always going to be down. Okay, so assume for some downtime, assume for some fault tolerance. So you can never assume have single points of failures because of this. Otherwise, your whole system is going to stop working. Okay. Now, this is not the case if you have a small system. If you have 3 nodes, it's not the case that at any point in time one of the nodes is down. You will have long periods where all 3 nodes may function and occasionally something may go down. But as the number of machines grows, that is no longer the case. It's something to keep in mind in any large distributed system. Is that clear? Okay. So now I'm going to talk a little, give you a different perspective on fault tolerance as to why this is important. Okay, so as computer scientists or computer engineers, we know that machines that we build, software systems that we design are not very reliable. Okay? Software will have bugs. Okay? Machines tend to hang or crash from time to time. Okay? And we tolerate it by saying, I'm going to just reboot the machine and the problem will fix itself. Okay? This is inbuilt for inbuilt reaction to something going wrong. Okay, machine is slow. Let me restart. Maybe it will, whatever problem is going to go. So this is how most computer science approach this problem. But if you now see that computing is becoming pervasive, okay? Everybody has access to some computing device. It could be a phone, it could be a tablet or whatever else. You may have a set-top box. Okay? You can no longer operate with this assumption. Okay? Most people who are not computer scientists are not programmed to think or not designed to think something went wrong, let me restart. This is not what they expect. Okay? Most other devices that you encounter are not designed this way. You don't buy a TV and say every 10 days I'm going to restart my TV, or my car is not going to be reset every 10 days. But your computer maybe have to be reset every 10 days because we built our systems to be inherently unreliable. That's not how you build a car. Okay? Nobody is going to buy cars if they have to do some reset every 10 days. Yet, that's what computing devices give you. Okay? And the reason for this is when you design software systems, you often neither take into account issues of failure, nor do you take into account issues of security. All of these cause problems because now when it was only computer scientists using computers, it was their own tool as one thing. But now everyone else uses it, they are not used to this kind of problems. Okay? They are used to much higher degrees of reliability which are never have been traditionally built into computing systems. Okay? But this though does happen, right? So now you have a large banking system, lots of online users. If you build your system this way, every so often your bank system goes down, your users are going to be really upset with the bank because they expect the system to work. They don't expect to go to an ATM because the ATM is just a Linux computer system says, okay, I'm rebooting, wait for 10 minutes. Okay, you just expect it to work like you expect anything else to work. Okay? So what this says is as distributed systems become bigger and as systems become more and more pervasive that non-technical users start using them, they are not used to this mode of operation that computer scientists seem to take for granted, which is let's ship software that has bugs. Let's assume that things are going to fail. We are simply going to restart it and continue. That's not going to be the case. You have to make your systems more reliable. Okay? This requires you to rethink how you write programs. Okay? Because people depend on them and they don't expect that it's okay for the program to hang every so often and so on. Okay? But that requires you to write reliable code. If your code is not reliable, you at least make your system reliable by replicating it and so on. So this problem has become a lot more important, as has the problem of security, which is the other problem that is caused by bugs and so on. Okay, this, credit card information gets compromised and your private information gets compromised because our systems are not secure, just as they are not reliable. Okay? So these two fundamental issues seem to be causing a lot of problems. So the thing to keep in mind is these issues require a lot more attention. You cannot just write a program and assume that it's not my job to ensure it's reliable or bug-free or robust from security breaches. It is a problem, okay, for all systems designer or computer scientists. So with that perspective, I'm going to now talk a little bit about basic concepts. Okay, so what we need are more reliable and more dependable systems. Okay? How do you design them? Okay? You can't suddenly assume that all programmers are going to stop writing code without bugs. Okay? That's not going to happen. Yet you want your system to be reliable. Okay? So you'll have to think about more carefully about how do you go about doing this. Okay, so in this context, we'll talk about several different metrics. One is availability. Okay? Availability says system should be available for use at any given time. Yeah, well, so that's simply a matrix saying any user accesses the system, is it up or not? Okay? Availability is measured in terms of percentage. Okay? So here is a system that is 99.999% available. Okay? So this is referred to also as 5 nines of availability. If you're 99.99 available, that's 4 nines. If you're 99.9 available, that's 3 nines of availability. The most reliable systems that we have built today have 5 nines of availability. Okay? 5 nines of availability says that in each year you can tolerate no more than a few minutes of downtime, no matter what happens. The system is up for, by and large, for the whole year, barring a few minutes. If you're 99.9, you have a few hours of leaving. Okay? Anything about 99 means it's highly available. Okay? These are the most available systems. Okay? So if you have that kind of availability, that says your downtime is going to be very low. But how to design such systems is a different problem. This is just what kind of guarantees you can give on your system. Okay? Large numbers of systems have nothing close to this at all. Okay? But this is what many systems have achieved. Nothing has gone to 6 nines of availability. Once you get there, basically it says you can't have any failure at all. Okay? 5 nines are the best systems you have built. If you even get 99, you should be happy. But this is what you should strive for in general. Okay? So that's availability. Okay? Reliability is a related concept to availability, but it just says system should run continuously without failure. Okay? Failures can happen, but system should continue to function. I mean, it has to basically overcome those failures in some way. Okay? Safety is a related property also, which says you can assume that there some components may fail, right? But the overall safety of your system cannot be compromised. You cannot have catastrophic failures just because some smaller components. Okay? Very mission critical applications have to guarantee high degree of safety. Okay? Let's say a computing system that's going to fly an airplane. Okay? You want to ensure that even if something small goes wrong, you can't lose control of the plane. That's going to have catastrophic consequences. Same as, let's say, a computing system that runs a nuclear power plant or anything like that requires a very high degree of safety. Can't say reboot the system while the system is rebooting, the system doesn't work. Okay? The system as a whole doesn't work. You cannot have that kind of scenario. Okay, so you want to ensure that you have safety at least for mission critical applications. Okay? Maintainability also says if some parts of the system fail, how quickly can you swap them out or replace them or fix them. Okay? So ideally you want all of those properties. They're hard to achieve or very difficult to achieve. So you want highly available systems, you want highly reliable systems, and systems to be highly to have a high degree of safety, and they have to be maintainable. Okay? So those are all properties that if you strive for and design your system this way, you will actually have an end good design. Okay? But it's easier said than done because of all the problems I talked about. That is not how we have been designing software systems or even hardware systems to function. It requires a change of mindset. But while individual components continue to be unreliable, can you still build a distributed system that's reliable? Okay? So you are given unreliable components. The building blocks are unreliable. Your individual software systems may have bugs. The hardware may fail. But can you put it together with larger number of machines and replication that still makes the overall system available, reliable, safe? Okay? That's the only way to attack the problem. Okay? You can only do one of two things. Each component is highly reliable, highly available or safe, but that's not going to happen because of the way we build system. So then you have multiple components, each of which can do things that the other components can do and take over whenever things fail. And that's the way we are going to do this in the context of fault tolerance. Is that clear? Any questions here? Okay, so I'm going to, since we have 5 minutes, I'm going to not go through more definitions, but I'm going to show you a voting example to build fault tolerance where individual components can fit. This is actually a circuit, okay, electronic circuit, not. So the top figure shows a circuit with 3 components A, B, and C. Okay, what the components are doesn't matter. We'll assume that some input comes to A does some computation using an electronic circuit, it produces an output that's fed to B, B does the same thing, feeds it to C. There are 3 independent components, A, B, and C, right, that are part of a larger circuit. Now it should be clear that there is, if any of these 3 components fail, the circuit as a whole is going to fail, okay, because that component stops functioning. Okay. Here is a fault tolerant version of the same circuit. So what you have done is you have replicated A as A1, A2, A3. So there are 3 copies of A. Okay. There are 3 copies of B and there are 3 copies of C. Okay. What we will do is each input is now fed to all 3 copies. They're all going to perform the same computation and then they're going to vote. Here majority rules. They don't have to agree all, but they have to, the majority has to agree. Okay. So if one of these components fails or becomes buggy, it starts producing garbage as its output. The other 2 are functioning right. 2 out of 3 is majority in this case. So the other 2 are going to override whatever it does and you'll still have the right answer. Okay? So you need a voter between 2 stages. The voter takes the input from the previous stage, okay, and it basically checks, compares them and takes the majority and sends that as its output. Okay? So all this is doing is comparing. As you'll see, each of these 3 are going to feed to each voter. The voter is simply going to compare the inputs. Okay, if this is a bit, your answer is 0, 1, whatever computation you do, you simply compare. Okay, and whatever the 2 values you get, your part, at least 2 will agree. Okay, in this case, because only you can tolerate 1 failure, so you take the 2 and you send it. If all 3 agree, that's also fine. Okay. Now you will see that if you had only put 1 voter here, that would be a problem. So voter is also a circuit. Okay, so if you have an unreliable voter, that's a single point of failure. Even though all of these 3 components may be performing their task, if the voter fails, it may start producing garbage. So what you do instead is the voter itself is replicated. That's an important concept. You can't say I'm going to replicate the main component, but there is a single voter that's going to decide what is the majority. Because that's a component also that can also fail. Okay? So this is what you mean by when you build fault tolerant system, you can't replicate some key components but not replicate some other maybe other components, because if those components are faulty, the circuit can still fail. So as a result, what we have done is every input is fed through all of these, every output is fed through 3 voters. Okay? And each of these voters is going to feed one of these stages. Okay? So one voter fails, that means that the next stage, that component is going to get garbage value, but the other 2 voters are fine, so these 2 will be fine, and so on. Okay? So in this case, no matter what happens, if one component fails in each stage of the pipeline, the circuit as a whole is still going to function. Okay? So this circuit can handle 1 fault per stage, by stage meaning either stage A or the voting stage for A, B, and so on and so forth. Okay, is that clear? So this is referred to as triple modular redundancy. Okay, there's 3 levels of redundancy. We made 3 copies of every component in your system. Every input and output were fed to multiple copies so that no matter what fails in the system, the circuit as a whole continues to function. Okay? Now having said that, it should be clear if there are 2 failures per stage, you will still get bad output. Okay? This circuit can handle 1 failure. So you have to engineer your system to design the maximum number of failures you want to tolerate. Anything more than that will still cause trouble. Okay? This can tolerate 1 failure. 2 failures, you are in trouble. But that's okay. You said that you designed it for 1 failure and that's what you care about. Okay? So this is called TMR, or triple modular redundancy. Now the reason I'm showing you this very simple circuit is we are going to use the same principle. Okay? We are going to replicate the components. We are going to use voting and agreement. Okay, so there's a voter here. Same kinds of things we are going to start talking about in the context of distributed system. This is a good scenario. This is what most people would do if they don't want your system to be fault tolerant. You will have a sequence of components in your distributed systems. They all communicate with one another, but there's no redundancy. If any component fails, the system fails. Okay. So what we will end up designing, if you want to make it fault tolerant, will look something like this, or you will have even more replicas if you want to tolerate n failures instead of one failure. Okay. So this is just a good principle to keep in mind as to what is coming down for the next few lectures. Okay, any questions here? Right. So I'm going to stop here. We're out of time. Okay, so we'll continue this next time.